All right, everyone. In this video, we are going to have a gentle introduction to the topic of functions of multiple variables. Now, to talk about what a multivariable function is, we have to make sure we have a really solid understanding of what a function is. And so we start there. A function, simply put, is a rule for taking an input and sending it to a single output. And so typically a function has a rule, I should say, for many different inputs, and it keeps track of them, sending them each to a single output. In a very abstract setting, I could imagine a input space, and these could be things like real numbers, 0, 1, 2, 3, 4, and so on. These could also be, even more abstract objects, though we won't really consider those right now. But we can define our function then, and I'll sort of write the letter F for my function here in the ether, is a way to take each of these different inputs in my input space and send them to a single output in my output space. So maybe my output space looks something like it has another set of numbers. Let's say 2, 4, I guess that looks more like a 9, 2, 9, 17, and 20. And so my function then will take my inputs and send them to single outputs. So maybe the number 0 gets sent over to the number 2. And if I were making a list of what my function did in the notation, I might say f of 0 equals 2. I might take the number 1 and I might send it to the number 9. And then I could say f of 1 is equal to 9, and so on and so on. Now notice the function is allowed to send multiple inputs to the same output. So the number 2, for example, could also go to the number 9, and then we could say f of 2 is equal to 9 as well. This is allowed. We can have multiple inputs going to the same output. However, we must ensure that each input is sent to a single output. And so what I mean by that is if I have already assigned f of 2 to be equal to 9, I cannot also simultaneously have f of 2 equal to 20. So I cannot have both of these things existing simultaneously. Each input, in this case, the input number 2, has to be sent to a single output. So it cannot go both to 9 and to 20. And so that would be not okay in this case. We would have to cross out that arrow. There's another common name for this feature of a function. In so many words, this is exactly the vertical line test, which you are familiar with. Right? So the vertical line test says that if I draw a vertical line on a graph and it intersects my function more than once, that means that I have a single input at the location of that vertical line being sent to two different outputs, and that is not allowed. So we must make sure that any vertical line drawn in our graph of our function only hits the graph at most once. Now, I'm already talking about graphs, and I'm talking about visualizing a vertical line in a graph. So right away, you have a sense that these functions are not always completely abstract. Oftentimes, we will graph these. And so I'm going to scroll down and talk a little bit about graphing. Now, as I do, I want to talk about the typical input and output example for a function. And what we have seen in most of our career up until this point is that the input space and the output space are sets of real numbers, aka points on the real number line. And so what that means is that if I have a function whose inputs and outputs are real numbers, so here I have the function f of x equals x squared, I'm imagining that my input values are real numbers. And I'm imagining that the output is just that real number squared, so also a real number. And so when my input and output sets are just sets of real numbers, I can often think about a graph for these. Specifically, my input real numbers are identified with the real number line that is the x-axis. My output numbers are identified with the real number line that is the y-axis. And so if I have an x-axis and a y-axis drawn here, well, okay, there we go, then my function can be graphed using the equation y equals f of x, or in this case, y equals x squared. So this is a visual representation in the xy plane of my function. And as we know, x squared is just a nice looking parabola. Now, again, the way that I am thinking about this is sort of simultaneously on my graph. If I look at the point, let's say this is x equals 2, I would plug in and I would get y equals 4. And so this is like saying f of 2 is equal to 4. And equivalently, we could say when x is equal to 2, y is equal to 4. Or if we were doing one of these, input output boxes like we had up above, this would be sending the number 2 over to the number 4. And we get something like that. Okay, but for a typical function, we are inputting just a single number. We are getting as an output a single number. In this case, the vertical line test truly is just a vertical line test. So I cannot have a single x value mapping to two y values. So each vertical line hits the graph at most once. And yeah, in this case, we have this nice graph that we can draw in a two-dimensional plane using x and y variables. All right, so we are going to generalize this now to multivariable functions. In multivariable functions, the input space can consist of not just numbers, but points in n-dimensional space. And so I want to highlight what I mean here. I'm going to just erase this piece to give myself a little bit more room. There we go. In my original function that I had drawn up above, my input set was the set of real numbers, and sometimes the set of real numbers, aka the real number line, is identified with this symbol. It is sort of a fancy mathematical letter R, and even more so, an R with a superscript 1. So the real number line is one-dimensional real number space, right? Then the real number line is exactly, it is this one-dimensional set of real numbers. So if my input and output spaces are both corresponding to real number lines, as we saw here with our x-axis and our y-axis, I can formally say that f is a function that takes input values in R1, that's just our single x value, and gives us output values that are also in R1, and those are just our single y numbers. So this is telling us that we have a x, and we're sending it to a y. And this is not defining the function. This is just kind of stating what type of function we're looking at. The actual function is still the function f of x equals x squared. It's given by this analytic formula up top. So in multivariable functions, the input space can consist of points in n-dimensional space. Well, schematically, what that might look like is n-dimensional space. I'm going to write that as Rn, like this. And Rn is just the set of ordered numbers, x1, x2, ... up to xn. So it's a list of ordered real numbers, and there are n of them. And so the space of all R sub n is the set of all such ordered lists of numbers like this. So specifically here, a multivariable function, as I am defining it, is one where my input space could be a general Rn, and my output space is typically R1. So I can plug in multiple real numbers as my input, and I get a single real number as my output. Now that is what we get in full generality, but let's take a look at a specific example, and it's the example that we see here. And I gave myself a little bit more space to say this will be a function from R2 into R1. And so to highlight what I mean here, again, if I'm just looking at R2, R2 is going to be the set of numbers or set of points in two-dimensional space. That's the set of points in the plane. And it's the set of objects of the form x1, comma, x2. And that is absolutely correct. What we will often do if we're just working in two-dimensional space is instead of using x1 and x2, I'll use the much more familiar xy. So my domain in this multivariable function is the set of points in the xy plane. And what I'm doing is I'm taking a point, x comma y, in the plane as my input. And for this particular function, I'm getting a single number as an output, and it's the number that is x squared plus y squared. So this follows a rule of a function. It sends inputs to single outputs. It's just that our set of inputs is more complicated now. A single input is a ordered pair of numbers. It is both an x coordinate and a y coordinate. And what we will see is that we can still work with these kind of functions. We can still even graph these kinds of functions, though our graphs become more complicated. And, just to sort of think through it, a single variable function like we saw up above had one-dimensional input, one-dimensional output, and we needed 2 dimensions to graph it. So here I have a 2-dimensional input and a 1-dimensional output. I can create a graph, but I will need 3 dimensions to graph it. And so we'll give this a try right now. I'm going to need to draw for this multivariable function a picture in 3-dimensional space. And so I'm going to have a picture that looks roughly like this. Here, my 3-dimensional space is usually identified not as the xy plane, but as x, y, z 3-dimensional space. And so in this case, I am going to have as my input 2 values, a single point in the plane, aka 2 real numbers, an x and a y, and my output is going to be the single number x squared plus y squared, which in my graph will take on the role of z. So just like up above, and I'll scroll up here for a quick second, just like up above, we said y is equal to f of x, and so our points were the points y equals x squared. So too, down here, I can say that f of x comma y will equal my z value. And so we are looking for the set of points in 3-dimensional space for which the z coordinate is equal to the x coordinate squared plus the y coordinate squared. And we will get into different strategies for graphing these down the road. But I want to introduce this first example. The function f of xy equals x squared plus y squared has a graph that is a 3-dimensional generalization of our parabola up above. So I can't draw it all, of course, because it goes off the page and continues up forever. But this 3-dimensional parabola is often called a paraboloid, and it is one of our early and most important multivariable function graphs. So going forward, we're going to look at more multivariable functions. We're going to talk about strategies for graphing them. And then in short order, we're going to talk about ways in which we can apply calculus to these, computing derivatives and integrating multivariable functions. But that's going to do it for this video. Thanks so much for watching. See you next time.